All right, guys, now we have some notes and examples on sound intensity level. The key word here being level, okay? Sound intensity is measured in watts per square meter, but sound intensity level is measured in this kind of silly unit called decibels, which is actually 1/10 of a bell. And this is named for Alexander Graham Bell, the guy who invented the telephone. And so before we get into decibels, let's talk about human hearing a little bit. The threshold of human hearing, the smallest sound or quietest sound that we can hear, is about 1 times 10 to the minus 12 watts per square meter. Okay, I've always heard this defined as the sound of a mosquito at 10 feet or 3 meters. Okay, pretty small, 1 times 10 to the minus 12 watts per square meter. And the threshold of pain is about 10 watts per square meter. This is a really loud sound, hurts our ears. Okay, and so this system of sound intensity level is defined in decibels. It's given the symbol beta, and it's equal to 10 dB, 10 decibels, times the log base 10 of the intensity of the sound that you're interested in giving the level of, divided by I0, or a reference intensity. And this reference intensity we use is the limit of human hearing, or the threshold, which is I0 is equal to 1 times 10 to the minus 12 watts per square meter. Okay, so when the sound that we're interested in, I, is equal to this quiet sound, we end up with 0. When I is equal to I0, beta, or the intensity level, is equal to 0 dB. And so one of the reasons we have this system is because in studies humans will find that a sound that is 10 times more intense, meaning instead of having 10 to the minus 12 watts per square meter, we have a sound that is 10 to the minus 11 watts per square meter. Humans tend to perceive that as being twice as loud. So every time we say, ah, yes, this signal or this sound is twice as loud as the other sound, that involves about a factor of 10 in terms of its actual intensity. So that's why we have this logarithmic scale to describe the sound intensity level. So what about when the intensity is equal to the intensity of the pain threshold? Or in other words, what is the sound intensity level at that case? We get that beta is equal to this 10 dB times the log base 10 of our sound that we're interested in, which is 10 watts per square meter. That's the intensity of sound at the threshold of pain, divided by I0, which is 10 to the minus 12 watts per square meter. We end up that beta is equal to 130 decibels. So a sound of 0 decibels we can barely hear in a quiet room. A sound of level of 130 decibels is considered painful. So plus 10 dB in sound intensity level. So if we add 10 dB in sound intensity level, that corresponds to an intensity increase of 10 times. So another few examples, 70 dB would be a sound intensity of 10 to the minus 5 watts per square meter, and 80 decibels would be 10 to the minus 4 watts per square meter, 10 times more. Okay, so every 10 decibels increases the intensity by a factor of 10, and 0 dB is the limit of hearing, and 130 dB is the limit or the threshold of pain. Okay, so now I want to do an example that includes both intensity and decibels. So for the example problem, the sound intensity of a blender at a 5-meter distance is 83 decibels. What is the sound intensity level if another blender is turned on? All right, well, we're going to use our expression for sound intensity level. Beta is equal to 10 dB times the log base 10 of this intensity that we're interested in divided by the reference intensity I0. Now, just as a reminder, when we're dealing with base 10 logarithms, in order to kill this base 10 logarithm, we need to raise both sides. We need to take 10 and raise both sides by that power. So if we do 10 to the raised to both sides, we end up with 10 to the beta on the left-hand side is equal to, actually, we need to get this log by itself. So we're going to divide both sides by 10 dB. On the left-hand side, we end up with beta divided by 10 dB. On the right-hand side, we end up with the log of the intensity ratio. Now we can take 10 and raise both sides to that power. So on the left-hand side, we're going to end up with 10 to the beta divided by 10 dB is equal to the ratio of the intensities on the right-hand side. So now, solving for the intensity due to that one blender, we're going to get, let me rewrite that expression. We get 10 to the beta divided by 10 dB is equal to the intensity divided by the reference intensity. Or the intensity of that one blender is going to be equal to the reference intensity times 10 to the beta divided by 10 dB. And we're told that the one blender gives a sound intensity level of 83 decibels. Okay, so this can be rewritten one more time as I0 times 10, and this is 83 divided by 10, so this is going to be to the power 8.3. So this is 8.3, and so that gives us our reference sound, I0, which is 10 to the minus 12 watts per square meter, the limit of human hearing, times 10 to the 8.3 power, right? This is almost a billion times. 10 to the 9 is a billion. So this is a billion times more intense than the limit of human hearing. And so this gives us the intensity of that one blender is going to be equal to 2.0 times 10 to the minus 4 watts per square meter. Now, if we have two blenders, we'll call that I prime is going to be equal to 2 times I. So I prime is equal to 4 times 10 to the minus 4 watts per square meter. Now we want to figure out the sound intensity level due to this amount of intensity. So the two blender, how many decibels does that give us? So we're going to get that beta is equal to 10 dB times the log base 10 of 4 times 10 to the minus 4 watts per square meter divided by our reference sound, which is 1 times 10 to the minus 12 watts per square meter. So we get that the sound intensity level due to two blenders is equal to 86 decibels. 86 decibels. So here we have doubled the amount of intensity, and we went from 83 decibels to 86 decibels. So in general, doubling the intensity increases the sound intensity level by +3 decibels. So as a follow-up question, what is the sound intensity level if we increase our listening distance of those two blenders to 10 meters? Okay, so now we need to figure out what the intensity is going to be as we increase our distance. So this goes back to the power and intensity that we were talking about before. And so now we want to say, what is the intensity going to be at 10 meters? So the intensity at 10 meters compared to the intensity at 5 meters is going to be equal to the radius at 5 meters squared divided by the radius at 10 meters squared, which is going to be 25 divided by 100, which is equal to 1/4. So as we move away from the blenders and we increase our radius from 5 meters to 10 meters, the intensity is decreased by a factor of 4. Okay, so now we need to plug that into our expression for beta to get the sound intensity level, and that's going to be 10 decibels times the log base 10 of the intensity that we're interested in divided by our initial intensity, I0, or our reference intensity, the limit of human hearing, which is going to be equal to beta times 10 decibels times the log. Now, we figured out earlier that the intensity due to two blenders at 5 meters was 4 times 10 to the minus 4 watts per square meter. And so that means the intensity at 10 meters is going to be 1/4 of that. Okay, so that's going to be 4 times 10 to the minus 4 watts per square meter divided by 4 times our reference intensity I0, which is equal to 10 dB times the log base 10 of 1 times 10 to the minus 4 watts per square meter divided by 1 times 10 to the minus 12 watts per square meter. Okay, you can see there's a factor of 8 orders of magnitude between these two. So we're going to get that beta is equal to 80 decibels for two blenders at 10 meters.